Welcome you all in the lecture number 10 of Abstract Algebra MTL 6051. In this lecture, we will continue from the previous lecture, that is, example of the factor group, what is simple group, what is conjugate class, and class equation. Let us see the example related to the factor group. Z cross Z by H, and H is generated by 2, 2. This factor group is cyclic or not, right? This we have to show that whether this factor group is cyclic group or not, right? If it is cyclic group, then all the element of Z cross Z divided by H is generated by AB, right? This is generated by AB, right? See, what is Z cross Z? It is the ordered pair AB where A and B belong to Z. And what is the subgroup generated by 2, 2? That is En into 2, 2. Okay, where n belong to Z. Now see, what is n? If n is 0, then it is 0. If n is 1, then it is 2, 2. If n is minus 1, then it is minus 2, minus 2. Similarly, what is this? This is 2, 2. All the elements generated by 2, 2, right? And order of this is infinite. Okay, now see, what is Z cross Z by 2, 2? This is quotient group and written as all the element of quotient group, we know that of this type AH, right? A belongs to capital H, capital G. Then Z cross Z by 2, 2, all the element of this of the type AB plus H, where AB belongs to Z cross Z. Now see, what is AB? AB is any element like 0, 0, 1, 0, 0 minus 1, right? 2, 3, 5, 4, right? Then this is the some examples of this. Okay. Then what is the order of this? Order of this is infinite. Okay. Order of Z cross Z by 2, 2 is infinite. Okay. Suppose this is cyclic. Then what other group that of infinite order is cyclic? That is Z. Then Z cross Z by 2, 2 is isomorphic to Z. Okay. If this is cyclic, then this is isomorphic to Z. Okay. Now see, what is Z with respect to addition? Z with respect to addition is group, right? This is group, and order of 0, its identity is 1, and order of other element is infinite, such that A belongs to Z minus 0. Okay. Now see, Z cross Z by H, that is all the elements generated by 2, 2. Consider its two element. One is 0, 0 plus 2, 2. This is nothing but 2, 2. And this is identity. Identity of factor group G by H is H. Identity of factor group is H. Then order of this identity 2 2 is 1. Okay, now consider another element 1 1. Sorry, this is 1 1. Consider another element 1 1 plus 2 2. Okay, what is order of this element? Order of this element is 2. Why? Since 1 sorry since 1 1 plus 2 2 plus 1 1 plus 2 2. What is this? This is 2 2 plus 2 2. Okay, and what is this? This is 0. Sorry, identity. 0 means identity. Since we know that operation of quotient group a plus h plus b plus h is equal to a plus b plus h, right? See, a plus h, b plus h is equal to a plus b. What is 2? 2 is 1 1 plus 1 1, that is 2 2. Okay, then order of this element is 2 and order of this element is also 2. Means order of this is 1, order of this is 1 and order of this element is 2. It means z cross z by 2 2 has two elements of finite order, where z has only one element of finite order, that is 0. It means this z cross z by 2 2 is not isomorphic to z, right? If it is not isomorphic to z, it means this is not cyclic. Not cyclic. Okay, now come to the another example. See, z cross z by 2 4 is cyclic or not, right? This problem is similar to the previous problem. It is homework for you, right? Answer is not cyclic. This is not cyclic, but you have to find at least two elements. Find at least two elements of z cross z by 2 4 whose order is finite. Okay, in this way you can show that this is not cyclic. Proceed in similar way like the previous example. Now come to the another example. Whether we know that before going to the another problem, let us see what is set of integer with respect to addition. This is cyclic group. We know that this is cyclic group. And what is generator? Generator is 1 or minus 1. Okay, it means 1 is equal to z and 1 to the power k means k into 1, right? K times addition. Then this z plus is cyclic group. Now we have to show that whether if z is cyclic, then z cross z is also cyclic. This is also cyclic. Or z cross z is cyclic, right? See the example. Z cross z is not cyclic. See, let us assume it is cyclic. What is z cross z? Z cross z containing all the ordered pair AB such that AB belongs to Z, right? We have to show that this is not cyclic. Let us assume this is cyclic. If this is cyclic, then it is generated by it is generated by AB, right? It is generated by some element AB. Okay. Now see one example. First thing is that what is the relation between A and B? Either A equal to B or A does not equal to B. Yes. If A does not equal to B or A equal to B, then if A equal to B, then this type of element 1, 3, this type of element 1, 3 or 1, 5 in Z cross Z, if A equal to B, then we can't generate this type of element, right? So this is not generator if A equal to B. And if A does not equal to B, then 2, 2. This type of element cannot be generated by AB, right? In both the cases, if A does not equal to B, then this AB cannot generate this 2, 2 or 3, 3 or 4, 4 like this. And if A equal to B, then this cannot generate element of the type 1, 5, 1, 3, 2, 1 like this. Okay. In both the cases, this is not generator, right? Hence, Z cross Z is not cyclic. Okay. Now, see the factor group. What is Q? It is set of rationals. What is Z? Set of integers. Okay. Then, what is Z? Z is normal subgroup of Q. Okay. Then Q by Z exists. What is the condition for factor group G by H? H is normal subgroup of G. Then Z is normal subgroup of Q. This Q by Z exists. Okay. What is the element of Q by Z? Element of Q by Z is A plus Z. Okay. This Q is group with respect to addition. Okay. Now, element of Q by Z is A, operation, addition, and Z. Okay. What is A? A belongs to Q. Right? See this thing. Then what is element of Q by Z? Something like this. A belong to Q, 0 is rational, 0 plus Z. 1 by 2 is rational, 1 by 2 plus Z. Minus 1 by 3 plus Z. Right? 1 by 5 plus Z. Okay. What is the order of Q by Z? This type of infinite element are present in Q by Z. Therefore, order of Q by Z is infinite. Okay. If Q by Z is cyclic, we have to show that it is cyclic or not cyclic. Let us assume Q by Z is cyclic. This Q by Z is cyclic. It's our assumption. If Q by Z is cyclic and order of Q by Z is infinite, then this Q by Z is isomorphic to Z. Okay. Then what is the element of 0 plus Z? What is the order of 0 plus Z? 0 plus Z is the identity of Q by Z. Then order of identity is 1. Order of 0 plus Z is 1. Okay. What is order of 1 by 2 plus Z? Order of 1 by 2 plus Z is 2. How? Same way. A plus H, quotient operation. And B plus H is equal to A plus B plus H. What is H here? Z. What is A here? 1 by 2. What is B? 1 by 2. Now apply this operation. 1 by 2 plus Z, 1 by 2 plus Z is equal to 1 by 2 plus 1 by 2, that is 1 plus Z. Right? And 1 plus Z is equal to, since 1 is element of Z, therefore 1 plus Z is equal to 0 plus Z. That is Z. Right? That is Z. What is 1 plus Z? 1 plus z is 1 plus what is z? 0 plus minus 1 plus minus 2 plus minus 3 that so on. Add this one here. 1 plus 0 1, 1 plus 1 2, 1 plus minus 1 that is 0, right? 1 plus 2 3 and minus 1 that so on. Means this set is nothing but 1 plus z is nothing but z. Okay, therefore order of 1 by 2 plus z is 2. Okay, order of 1 by 2 plus z is 2. Now 2 element order of 0 plus z is 1 since it is identity of q by z, and order of 1 by 2 plus z is 2. Okay, there are two element 0 plus z and 1 by 2 plus z in q by z whose order is finite, whose order is finite. Okay, then q by z is not isomorphic to z. If it is not isomorphic to z, then this is not cyclic. Okay, same thing is here. See, let us discuss the simple group. Later on we will discuss detail about the simple group. Here we focus only the definition and example of the simple group. A group G is said to be simple. A group G is said to be simple if G has only two normal subgroup. One is identity and one is Z itself. For example, Z3 with respect to addition modulo 3 has only two normal subgroup. Two normal subgroup, that is 0 and Z3 himself, right? Then by definition, this Z3 with respect to addition modulo 3 is simple group. Okay. Now, if G is equal to ZP, what is P? P is prime. P is prime. Then this G is simple, just like 3 is prime, then Z3 with respect to addition modulo 3 is simple. Okay. G is equal to Z10. Z10 with respect to addition modulo 10 is not simple. This is not simple group. Okay. If order of G is any prime number, what is P? This P is prime number. P is prime. Then this is always simple. Means any group of prime order is always simple group. Next, if order of G is P square, P is any prime number, right? Here P is also prime. Order of G is P square, then G is not simple. Then G is not simple. Okay. Later on, we will see that any group of order P square has one normal subgroup of order P. That is, its normal subgroup is one is identity, another one is G. These two are trivial, and one is H. Order of this H is P, right? Due to this H, this G is not simple. Okay. Symmetric group Sn. Symmetric group Sn. S1 is simple, right? S1 is simple. S2, S1 and S2 is simple. But S3, right? Proper normal subgroup of Sn, right? An. Every Sn, S3 has A3 as proper normal subgroup. Proper normal subgroup. Okay, then this S3 is not simple. This S3 is not simple. Okay, similarly ESN for n is greater than or equal to 3, it's always non-simple group. Always non-simple group. Okay, what is alternative group? In alternative group, A4 is not simple. A4 is not simple. Verify it. Okay, but n is greater than or equal to 3, but condition is that n does not equal to 4. Since A4 is not simple, an it means A3, A5, A6, A7 dot dot so on. They all are simple. They all are simple group. Okay, now see what is the conjugate element. Okay, what is the conjugate element? In group, any two element is conjugate. Suppose G is group and AB belong to G. AB are any two element of G. Then A is said to be conjugate of B, or vice versa. B is said to be conjugate of A. Right? A is said to be conjugate of B if there exists X belong to G such that B is equal to X inverse A X. What is X? X belong to G. Then this B is said to be conjugate of A, is said to be conjugate of A, conjugate of A, and this can be written as X B X inverse is equal to A. It means this A is conjugate of B, conjugate of B. But focus only this thing. This A is conjugate of B. If A is conjugate of B, then B is also conjugate of A. Later on we will prove in this problem. Right? Then what is the meaning of conjugacy? See one more times. If G be a group, AB belong to G. AB belong to G. Then A belong to G is said to be conjugate of B if there exists X belong to G such that B is equal to X inverse AX. Remember this relation. This is the relation between A and B. B is equal to X inverse AX. X belong to G. Right? This is the relation, and this conjugate relation is denoted by B conjugate A, right? Or A conjugate B. Okay. Then this relation is, what is this? This is relation, and this relation is ER, means equivalence relation. This is equivalence relation. Okay. If this is equivalence relation, then we have to show three property. We have to show that this conjugate relation is equivalence relation. Okay. Then reflexive property. Every element is related with himself. Why? Since A conjugate to A. Why? By definition, A can be written as E inverse A E. Right? What definition says that? There exists X belong to G. Right? There exists what is X here? X is E here. X is E here. Then A is equal to E inverse A. What is E inverse? E. What is AE? That is A. That is A. Okay. Then every element is related with itself. It is reflexive. See the symmetric property. A related with B. Then by definition there exists X such that B is equal to X inverse AX. Okay. B is equal to X inverse AX, and this can be written as X. If B is equal to X inverse AX, then operate X both sides. XB is X inverse AX, that is XB. What is X inverse? This is identity. This one is AX, and operate X inverse both sides. XB X inverse. This is X inverse, and what is this identity? Means XB X inverse is equal to AX. Sorry, A, right? Then this X can be written as X inverse inverse. Okay, same thing here. X inverse, that is X. B X inverse is A. What is X inverse? Since X belong to G, therefore X inverse also belong to G, right? Say X inverse is Y, right? Then this is Y inverse B X inverse. X inverse means Y. Y inverse B Y. It means what? It means B conjugate to A. If A conjugate to B, then B conjugate to A. This says that this relation is symmetric also. Now come to the transitivity. If A conjugate to B and B conjugate to C, then what is the definition? Then definition says that there exist two element X and Y such that B is equal to, by this, B is equal to X inverse AX and B conjugate to C implies this. Then this C can be written as C is equal to Y inverse, okay, Y inverse B. What is B? B is X inverse AX. This one is B, X inverse AX, Y. Now, this C is equal to Y inverse X inverse A XY. This Y inverse X inverse can be written as XY whole inverse AXY, right? By reversal rule, XY whole inverse is equal to Y inverse X inverse, right? C. What is X? X in G. What is Y? Y is also G. Then what is XY? Since G is group, therefore XY is in G. Then this relation shows that C or A conjugate to C. Okay. Hence, this conjugacy relation is equivalence relation. Now, remember class 1. In class 1, I already told you, if on any set, suppose this is a set, and we define a relation, say R. Sorry. If this is any set, we define a relation, say R, on set capital S, say this is S. And if we are able to prove that R is equivalence relation, R is ER, then S can be partition. S can be partition, right? That is something like this. S1, S2, S3, Sn. Okay. This partition says that S1 union S2 dot so on union Sn. This is S, and Si intersection Sj is equal to phi for I does not equal to j. Right? This is the meaning of partition. Then this relation, what is this relation? This is conjugate relation. Conjugate relation. This conjugate relation we define on group G. Then by this result, this group G can be partition. Then group G can be partition. Right? See the following example, how this group G can be partition. See the conjugacy class, right? These S1, S2, Sn, if we can partition it, this is S1, this is S2, and this is S3, so this is Sn, then S1 union S2 union Sn, this is equal to S, and Si intersection Sj, this is equal to 5 for I does not equal to j. Okay, this is the partition. Then what is S1 S2 Sn? S1 S2 Sn, these are the class, and known as equivalence class. This is known as equivalence class, right? Or this class can be associated with the name of the equivalence relation. For example, our relation is conjugate relation. Then if A belongs to G, then conjugate class, right? Just like we define here equivalence class, we call it here, since our relation is equivalence relation, so we call this class as conjugate class. Conjugate class, remember that conjugate class for any element A. Conjugate class for A is denoted by CLA, right? CLA, and is defined as Y inverse AY. What is Y? Y is element of G, right? Now see the example of conjugate class. If G is abelian, then conjugate class is singleton set. Why? Since AY is equal to YA, AY is equal to YA. See here, X inverse AX. Conjugate class of A is X inverse AX, X belong to G. X is any element of G. Then X inverse AX. AX can be written as XA, right? And X inverse X is identity, and this is equal to A. If G is abelian, then conjugate class of any element is singleton set. Now find the conjugate class of each element of D4. What is D4? D4 is R0, we know that. R0, R90, R180, R270, S, V, D, D dash. Right? All these operations we know very well. Right? We already discussed in our previous lecture. See, CL R0. What is R0? R0 is identity. Then conjugate class of identity is one identity only. Right? Always in any group, conjugate class of identity is only identity. Why? This R0Y is equal to Y. Right? This is Y. And Y inverse Y is identity. What is identity? R0. This is R0. What is conjugacy class of R90? Conjugacy class of R90 is X inverse R90 X. X belong to G. What is X? X is any element of G. What are the element of G? R0, R90, R180, R270, H, D, H, V, D, D dash. Okay. Then write all the element of this type. First X is R0, R0 inverse R90, R0. Then X is R90, right? Then X is R180, X is R270, X is H, X is V, X is D, X is D dash. Solve all this, you got this element. And what is this? R90 and R270, right? Then if conjugacy class of A containing element itself always there A and B, suppose this is A, B, C, then this is equal to conjugacy class of B and conjugacy class of C also, right? This is conjugacy class of B and conjugacy class of C also. Then CL of R90 is R90 R270, then CL R270 is also same as CL R90. Then CL R180 is R180. Okay. CLH is HB. This is also equal to CLB. And CLD is equal to DD dash. This is also equal to CLDD dash. Now see, CLR0 union CLR90 union CLR180 union CLH union CLD. Okay, what is CLR0? R0. What is CLR90? R90 and R270. What is CLR180? R180. What is CLH? H and V. What is CLD? D and D dash. Right? These all unions is this one. And what is this? This is nothing but D4. Right? This is the perfect example of partition. Okay? See one equation. That is order of CLA. Right? Evaluate conjugacy class of each element A and order of CLA and take summation for every element of G. This is nothing but this is order of G. Right? See in previous example. What is previous example says that what is order of CL0? It containing one element, that is 1. What is CL of R90? It containing two element R90 and R270, that is 2. What is CL of R180? It containing one element, that is 1. What is CL of H? It containing two element H and V, 2. What is CL of D? Order of CL of D, D and D dash. Right? It containing two element. Right? What is the sum? Sum is 8. It means this equation says that, right, CLA, first evaluate CLA for all A belong to G. Evaluate CLA for all A belong to G and take order of every CLA and took summation, and this is nothing but this is order of G. Right? Later on we will study this is nothing but this is class equation. This is class equation. Okay, but see the another example. What is Q4? Q4 is this. Right? What is CL1? Since 1 is identity, therefore this is 1. Okay. What is CL of minus 1? CL of minus 1 is minus 1. Okay. CL of 1 is 1. CL of minus 1 is 1. What is CL of I? This is I and minus I. What is CL of J? J and minus J. Remember that if CL of A is ABC, then this is also equal to CL of B and CL of C. Okay, this CL of minus J. CL of K is equal to K minus K, then this is CL of minus K. Now, then verify the above equation. CL order of CLA for all A belongs to Q4. Q4. This is equal to order of Q4. Why? Check. What is order of CL1? 1. Right? What is order of CL minus 1? 1. What is order of CLI? 2. What is order of CLJ? 2. What is order of CLK? 2. This is equal to 8. And what is order of Q4? That is 8. Right? So this equation is verified. Similarly, if G is equal to this, what is this? This is GS3. Then CL of I is identity CL of 1, 2, all cycle of length 2. 1, 2, 1, 3, 2, 3. Right? But you solve this one. Okay? This is homework for you. Solve this. CL12 is equal to 1, 2, 1, 3, 2, 3. Right? Similarly, if 1, 3, 2, 3 is here, then CL13 and CL23 is also same. CL12. Okay. CL123 conjugate class of cycle of length 3. It is all the element of length 3. Right? Then 1 2 3, 1 2 3 and 1 3 2, this one. Then S3 has three conjugate element, CLI, CL12 and CL13, right? CL order of CLI is 1, order of CL12 is 3, order of CL123 is 2, and this is equal to 6. Okay, then above equation, the equation summation over A belongs to G, order of CLA is equal to order of G is verified for S3. Okay,